Ok. Ok. Alô? Tá saindo algum lugar?
É isso mesmo.
Alô? Pronto. Muitos problemas para controlar. Daniel, com você agora.
Okay. So yeah, it's a huge pleasure for us to receive Professor Waisitai here in Brazil. It's the second time he visits Brazil, and we have been discussing for a long time online, and finally it's very good to have Waisitai here in person. So Waisitai is Emeritus Professor in the Department of Mathematics at the University of Singapore, right? And he did his PhD at Harvard, and he told us a funny story that when he graduated, he could choose between math or computer science degree, right? Because computer science was just emerging, but I picked the right choice. Which was math, but now we have the pleasure to have him in many computer science venues, right? Including now in the electrical engineering computer science computer department here at UFRJ, right? And so Ty research interests are in performance modeling, database systems. He was involved in startups, Microsoft, spent sabbaticals at Princeton, MIT, SLA, National Taiwan University, and he won several teaching awards. So he has authored a book, Analytical Performance Modeling for Computer Systems, and also actually two books, one is Locking Performance in Centralized Databases. So yeah, Ty has been also very active in these educational venues as well, like workshops on teaching, performance evaluation, and I think he's really a great mentor and colleague. So thanks a lot for being here.
So I want to thank the two Daniels for organizing this workshop. And just since this is on YouTube, I must advertise for it. That advertisement in videos. So I want to talk about something that has been an obsession of mine, which is cash misses. And my since he mentioned that people are being sucked into this black hole of machine learning, right? And I'm one of those who have not yet been sucked in. And I don't know I will be, but I have not yet been sucked in. And to me, there is a scientific issue here. If we call ourselves computer scientists, then we should do science. But machine learning, as far as I know, up to this point, is very engineering. I don't see how the things that we are looking at now will still be relevant 25 years from in contrast, if you look at something like cache misses, the first paper on cache misses that I know of, the Beladi's anomaly paper, was more than 50 years ago. And although it's such an old topic, there are still issues that are unresolved regarding cache misses, and people still write papers on cache misses. So to me, it is a fundamental problem in computing technology, and as scientists, we should contribute to building a science about this technology. Every time a new technology comes along, there's a caching issue. Whether it's a software technology or whether it's a hardware technology, and you see some of that later on. So caches are such a fundamental aspect. Now, what are the fundamental resources in the computation? The processor, the memory, the bandwidth. It's not that many, and memory is one of them. So if we want to build a science about computer science or computing technology, we should start with either the processor or the bandwidth or the memory. And this is my contribution. Trying to build a science around caches. So this line of work go back 25 years. A long time in computer science, but it has held up for 25 years. The last thing that I did for this was just this year. So over 25 years, I can every now and then come back and say something about caches. So that's something. It's because of that, it's a long list of collaborators. Most of them are students. A lot of them are actually undergraduates. Okay, so cache analysis has been around for a long time. Many papers were written about caches, but they were done in a what I call bottom-up fashion. So what do I mean by bottom-up fashion? You start with some number of assumptions, right? You assume that there is a LRU replacement. You assume there are no co-misses, no writes. Let's say you assume all the objects are of the same size. You assume independent references, etc. You make whatever necessary assumptions. Whatever assumptions are necessary, and then you analyze the interaction of these assumptions, and then create the equations. This is what I call a bottom-up modeling for caches. Mathematically, it is maybe the right thing to do. Scientifically, it's hopeless. Over these 50 years, we have done so much has been written using this bottom-up approach, but where have we gone? Where are we now? We are still as primitive as ever regarding the behavior of caches. Scientifically, we are as primitive as ever. So, what is the option? My alternative, the alternative that I offer is something that I call top-down modeling. I will not assume a particular replacement policy. I will not assume that there are no co-misses. I will not assume that the objects are of the same size. I will not assume that there are independent references. Then where do I start? I have nothing, right? So I do it top-down. The way I look at it is that the probability of a miss is a function of the cache size with 4 parameters. Just give me 4 parameters. No. And then there you are. There is the equation. And this equation is going to last for the next 40 minutes or so. Okay, so what are these 4 parameters? What are these 4 magic parameters? Okay, so the cache size is here. Now, one important parameter would be m star, which is the ideal m value. If you plot the miss probability against the cache size, then the data will come down. As you have more cache, the probability of a miss will be going down, and then at some point it will stop going down. Okay. At the point at which it stops going down, this is my m star value. If you increase the cache size beyond this point, you're just wasting memory because the probability is not going to go down anymore. If you decrease your cache size below this value, you're going to take misses. So this is, in some sense, the optimal, the ideal memory size. Okay, so that's the m star value. All right, they know what's the P star value. Okay, P star value is just the co-misses. Right? No matter how much memory you allocate for me, I have to take this amount of co-misses. These are the objects that you have to retrieve from external storage. Okay. What is this MV value? This MV value is a vertical asymptote. It could be positive or negative. In the case where it's positive, the interpretation is that this is the amount of space. No, I'm sure you have applications where it gives you an OM out of memory, right? If you decrease the memory allocation beyond a certain point, the workload just cannot run. So the MV value corresponds to that. And then what is this PC value? Oh, this is where all the magic happens. Dynamic allocation, prefetching, replacement policy, all of that is going to influence the shape of the curve. So the PC here determines the curvature of this curve. Okay. So this is the equation. The first time when this is the paper that proposed this equation, and we started out by testing it in operating systems. So we actually measured block reads from hard disk. This is not a simulation. This is you do a compilation, you do the measurement. Okay. So we instrumented the Linux kernel to alternative. There's a stop kernel replacement policy. We instrumented it to change the replacement policy to FIFO and random replacement. The workload is GCC. We compile the Java compile. Okay. So because the operating system had 3 alternative replacement policy, of course, when you run this workload, you have 3 different sets of data points. And the equation was able to fit all 3 sets of data points. Okay. So to have the equation fit the 3 sets of data points, that means that the parametric values must be different. Okay, and sure enough, for each one of them, the M0 values are different. This is the vertical asymptote on the other side. The N star, so these are co-misses. The co-misses are the same for all of them, but then the M star values are different for the 3 of them, which says that the replacement policies affects the M star, the ideal M value. The first time people look at this equation, they think that the M star value is the working set size. No, it's not a working set size. Because the working set size is a property of the reference pattern. Whereas this M star value is affected by the replacement policy. If you have a sequential reference pattern and a very smart replacement policy, then the replacement policy will just give you a 1 page. Right? Whereas if you look at the working set size, the working set size would be no matter how big the window is. So no. So the M star value depends on the replacement policy. The paper itself went through a whole bunch of other experiments, but let me move on to the first. Now, after we got this, I thought, okay, so how about we apply it to some other kind of cache? And the first one we tried it on was the database record buffer. So the database record buffer, you have multiple transaction classes that share the buffer. You allocate memory, allocate the buffer to these are called buffer pools. You allocate buffer pools to each one of the transaction class. And to motivate the problem, we look at the question of, okay, so you have allocated, you have partitioned up the buffer pool, and then some other transactions start. When other transactions start, you have to reclaim some of the buffer space that was allocated out, and then give it to the new one, right? Then the question is, how do you do the reclamation? How much to take from each one of from the existing transaction classes? You want to reclaim the memory in a fair fashion. Okay. So this is the idea, right? Let's say you have 3 transaction classes, and then you start this is the time, and then this is essentially the probability of a miss, normalized by co-probability. Then you see that initially for these three epochs, for example, it is unfair. It's unfair in two ways. First, that there's a big spread in the probability of miss, and it's unfair in that one particular pool is always has the minimum probability of a miss. Okay, now a new transaction class arrives, so it's unfair. A new transaction class arrives, and you want to free up some amount of memory. And so you, in order to free this one up, you claim some from here, claim some from here, claim some from here. And notice that in this particular case, the claiming is actually negative. You're actually increasing this. So the equation is supposed to figure out how to do the reclamation, whether the reclamation is going to be positive or negative. And then what you want to do is to make it fair. Since I have a closed form equation, I can do freshman calculus on the equation to figure out what the optimum allocation is. And the reclaim amount turns out to be this. It's kind of proportional to the amount of remaining memory, etc. You just scrutinize it, but it's not quite. Right? This is the proportionality. It's not proportional. It's not proportional to what you already have, which is the NI value, and it's not proportional to what you should have, which is the M star value. Rather, it's proportional to the difference of these two. But never mind. The important thing to note here is that I have an explicit form for how much to do, how much reclamation you should do. It's not any kind of iteration. Okay. So once you have that equation, once you figure out the amount to reclaim, you enforce that and you see that the range is smaller now, and none of the pool is consistently smaller. So in that sense, it's fair. So that's good. I think that the equation, although was derived for operating system page cache, actually applies to database record buffer. So the next thing is to apply it to garbage collection. So for garbage collected applications, this is particularly difficult to handle. And the reason is that if your application uses the garbage collected language, then there's something called the heap size. Depending on the memory allocated, the heap size will change. The garbage collector will allocate the heap size depending on how much memory allocated. So the heap is where you keep the dynamically allocated object, and then when the objects are idle, unused, and then you're under memory pressure, the garbage collector will come around and take away all the stuff. But the application, or in this particular case, the mutator, the name for it is the mutator. The mutator doesn't do any of this memory management. Okay. So where is the problem? The problem is that when you change the memory allocation, the heap size will change, and if the heap size changes, the garbage collector behavior changes. If the heap size is small, then the garbage collector has to work very hard. If the heap size is big, then the garbage collector can have an easy time. Which means that when you change the memory allocation, so you have the mutator reference pattern like this. Mutator reference pattern is like this, and then there is the garbage collector reference pattern. And when you change the garbage, the heap size, then the garbage collector reference pattern changes. So that means you look at the reference pattern itself. The reference pattern depends on the memory allocation. This is something that none of the bottom-up techniques can handle. How do you go about modeling the reference pattern, taking into account the behavior of the garbage collector when the heap size changes? How do you how do you inject this garbage collector reference pattern into the application reference pattern? Bottom-up modeling cannot deal with this. Okay, so my equation doesn't worry about this. It's just go ahead and do the fitting anyway. Okay, so first of all, so the issue, the way I motivated this paper was to say, okay, how can my equation help you decide how to set the heap size when given a memory allocation? So what I want to do is understand how the equation can help me size the heap. So in order to do that, I need to understand how the heap size affects the execution time. So initially, as the heap size increases, when you have a bigger heap, then there will be less garbage collection. With less garbage collection, there will be smaller garbage collection time, and therefore your execution time goes down. Good. But then there's a memory allocation here. And then when the heap size reaches the memory, gets close to the memory allocation, when your heap size gets close to the memory allocation, you begin to take page faults. Page faults are very expensive. So, boom, it goes up. Execution time goes up because you're taking page faults. After that, then again, your heap is bigger than the memory allocation anyway. You're going to be taking page faults anyway. But it is still true that the bigger the heap size is, the less garbage collection you're going to do, and since you have less garbage collection, you also have a smaller IO time. So this is the general behavior of this. How does this affect the heap size? What is, given this particular picture, what is a good heap size to have? So rather than be very ambitious and have a big heap size, and therefore minimize the amount of garbage collection, what you should do is reduce the heap size, increase the garbage collection, never mind, but avoid the page faults. So based on that understanding, the intuition, you'll use the equation and you get this allocation. Okay. So as the memory allocation increases, the heap size should at first be maximum, and then it drops, and then it increases linearly, and then it flattens out. So yesterday I was discussing with Danielle and the student about similarity caching, and in similarity caching, it seems to have a similar issue where there's a certain Q factor, and then there's a memory allocation. But the way the problem was formulated doesn't quite fit this particular picture, but I was wondering whether a similar issue arises. That in similarity caching, perhaps there is this parameter Q that should be adjusted, should be tuned according to the memory allocation. And how do you tune that thing? And maybe by using my equation, we can address the issue. Assuming that my equation works for similarity caching, but I'll come to that later. Okay, so I have a heap sizing rule. How does it perform in reality? Again, this is not simulation. This is running code on real garbage collectors. So we tried two different garbage collectors, and then we tried two mutators at a time, concurrent mutators at a time. Again, this is a problem that bottom-up modeling cannot handle. In bottom-up modeling, right? Suppose you have a reference pattern for this application, you have a reference pattern for another application, and then you run the two applications concurrently. What is the reference pattern? Where do you start? Where do you start putting two reference patterns together? I don't know. I've not seen any model that can do that kind of thing. For me, I don't care. It's just a reference pattern. And then I'll just use the parameters. Okay. So in this particular plot of this is essentially the runtime with respect to the heap sizing rule. So this is the set of data points from the default Giles RVM heap sizing rule. And then this one here is from something called a Poor Richards Memory Manager. This is a memory manager that instruments the application, instruments the garbage collector, etc. Keeping track of memory pressure, etc. is very tedious stuff. Very manual, very tedious stuff. In contrast, the blue lines here are from the heap sizing rule without modifying anything. The only thing that it does is every time a garbage collector springs up, it will look at the heap, it will apply the heap sizing rule to size the heap. This means that sometimes when the workload is running, the heap is already not ideal, but with the heap sizing rule, it cannot do anything. It has to wait for a garbage collector to fire up before it changes the heap size. So this is why sometimes the blue line is above the red line. The blue line is above the red line because it is a very passive kind of heap sizing. It only waits for the garbage collector to come up. Okay, so the point here is that with the very passive heap sizing rule, you can still do as good as the very proactive, intrusive Poor Richards Memory Manager. Okay. So I complained about bottom-up modeling, right? And I claim to have top-down modeling. What is top-down modeling? So top-down modeling means I start off with an equation with 4 parameters, and these 4 parameters are calibrated based on some sample data points. Now, what do these 4 parameters mean? In this particular case, for example, the parameter that I'm really interested in is the heap size h. So what do the 4 parameters mean in terms of the heap size h? So top-down modeling means that once I know that the 4 parameters work, what I do now is express those 4 parameters in terms of the heap size. Then what I will have is an equation that expresses the performance in terms of page misses, etc., in terms of heap size. So in that sense, I'm going down. And if at the bottom there you want to refine the parameters some more, you can do that. Okay. So let's see how that works. So this is the equation. The equation can be written in a form in terms of probability of a miss or in terms of number of page faults. So this is the form where it's in terms of number of page faults. Now, the n star value here, which is the ideal cache size, can actually be expressed in terms of the heap size linearly. It turns out to be very straightforward linearly. But then that means I introduced 2 more parameters, A and B. But what is A? A actually depends on the garbage collector. If it's a marked suite, then A is 1. If it's a semi-space, then A is actually half. This whether it's 1 or it's half, this actually can be analyzed based on how these garbage collectors actually work. And then what's B? B here is some space overhead. No, space for the code, space for the stack, space for the VM, etc. So it's some space overhead factor there. How about the N naught here, the one that controls the curvature? Again, it turns out to be linear. Linear in terms of the heap size, but introduces another 2 parameters. Okay, so there's a C here. C is the memory taken off the free leaves during the garbage collection. And then the D here is implicitly defined by C. So this thing is a piecewise linear thing like this, and then this one is determined by C, and that one is determined by the minimum, and then the kink there is the one that determines it. The point here is that this is the original equation. If this equation doesn't have the parameter that you're interested in, then you express these parameters in terms of that parameter that you're interested in. When you do that, you're going to introduce new parameters, and then you jolly well go interpret what those parameters mean. So this is the idea of top-down model. Okay. The memory hierarchy has multiple layers. So the next question to ask is, okay, suppose I have two layers, two adjacent layers. For level 1, I have a mixed equation. For level 2, I have a mixed equation. Now I take these two levels and I look at it as a cache, okay? Which means that there will be another equation here. Now how are the three equations related to one another? So first off, this combined cache here has memory size that's the sum of those two, okay? That's straightforward. And then the rest of them, the other parameters here, these four parameters here can be expressed in terms of the values for the other two equations. So I have an explicit form that expresses a combined cache in terms of the constituent caches. Does it work? So the way we tested that was on this complicated system. So for hypervisors, was it that I forgot which hypervisor this was. There was this concept of a transcendent memory. Transcendent memory is a kind of memory that was that they introduced to manage the idle clean pages. With virtual machines, a lot of time the memory is just wasted, unused. It's allocated, but it's unused. So they want to better manage that, so they introduced the idea of a transcendent memory. Now, with that transcendent memory, suppose you introduce a non-volatile memory to enlarge your space of caches at this level. The minute you introduce non-volatile memory, you bring in a lot of problems. Because non-volatile memory has this problem of being sensitive to writes. So you have to be very careful about writing into non-volatile memory. And because of that, the replacement policy becomes very complicated. Here, the level 1 is the DRAM. And we have to split it into a put buffer and a hot region. And then the level 2, which is the non-volatile memory, has a clean region. We can just ignore this other part of it. But notice that this is a combination of FIFO, LRU, and LF. It is a complicated replacement policy. This two-level cache is a complicated replacement policy with 3 different replacement policies crunched into one very complicated reference pattern. How are you going to model this in a bottom-up fashion? You'll never finish doing it. It takes 5 months to come up with a bottom-up model for this. Any day I can just change another replacement policy, and then what you're going to spend another 5 months doing this? No, you can't do that. It's just not scalable. Okay, so with these 2 levels, now there are actually 2 objectives now. At this level, at the DRAM level, because it's overcommitted, if you look at all the workloads that are sharing the DRAM, you sum up all the memory they need, it's way bigger than the DRAM size. And the memory manager doesn't care, it just overcommits the memory. Okay. But so what you want to do is share the memory among the different workloads in a very fair fashion. At the NVM level, you want to make sure that you don't have too many misses. Because anytime you miss here, you have to go to disk. And if you go to disk, you're just killing yourself. Okay. So at this level, the objective is don't have a miss. At this level, it's a system objective, which is that share things equally. So again, yesterday when I was discussing similarity caching with a student, this picture came into mind, where you think about similarity caching, or maybe KV cache underneath. Is there a similar kind of issue? How do you share the memory space. We have two different objectives, possibly two different objectives, and then you want to optimize on these two objectives separately. So for this particular case, the equation, we use the equation to do this two-level optimization. For the level 2, the NVM level, there are 5 VMs altogether. For the two of them, for those two, the SLO is the service level, objective is the latency, and then for this other level is a systems objective where you want the DRAM, you want the NVM, etc. to be shared equally. Using the equation, we were able to make sure that the level 1 means probabilities are fair, okay? And then for the level 2, that they satisfy their latency objectives. So this is for NVM. About the same time I wrote that paper, there was this concept of content-centric networking. So in content-centric networking, so in classical networking, you set up a TCP connection, and then everything goes to the source, content source, and then you download from the content source. With content-centric networking, you don't do that. What you do is, if you want something, you send interest packets into the network. The interest packets get somehow routed into the network, but the router caches behave as caches. So when a router receives an interest packet, you look around and say, do I have this in content? If I have this content, I just send it to the requester without forwarding the interest packet back to the content provider. So in that particular case, because of that idea, the network becomes a network of caches, and then you don't have a straight connection to the source. What you do is just fire off interest packets, and then the content will come from wherever the interest packets can be found. For this kind of a network, since the routers are behaving as caches, the natural question to ask is, does the cache-miss equation work for the router caches? When I mentioned this to my PhD student, he said, you are crazy because your equation was derived with page faults. It works for database buffer, okay, but now you're talking about traffic. You're talking about internet traffic. You expect the equation to work for traffic? I say, oh, give it a try. So we look at 3 traffic classes, different class sizes, different popularity measures, shapes, and then CBR and non-CBR. CBR is constant bit rate. That means the requester will constantly fire off interest packets. No matter whether the content comes back, I just fire. Okay, so this is CBR. In contrast, for non-CBR, I fire an interest packet, I wait for the content to come in, then I fire next one. So it's non-constant bit. And then we try a dumbbell topology like this, clients on the all around, and then you have the clients can request contents from anywhere elsewhere in the network. Okay, so that means that you can have cross traffic. You can have traffic packet traffic this direction, packet traffic in this direction, and they share the same cache in between. Okay, and it could be multipathing. Okay, so I fire off interest packet in 2 directions. Oh, okay, so I fire off interest packet to Y. Then this router will then duplicate the interest packet to both directions, and then the content may come in from first 3 packets may come in from this direction, next 5 packets may come in from that direction, etc. So this concept of multipathing, impossible to model this in a bottom-up fashion. Cross traffic, multipathing, etc. For me, I don't care. I just apply the equation. So the first thing to do is to make sure that the equation actually works. for router caches. And yes, we have for these three traffic classes. You take the take a sample of the miss probabilities, and then you fit the equation back. And then once you do that, you can do it for router caching. For the first three epochs, the cache is just shared. Okay, no partitioning of any kind. You just fight over that cache. And then once I have after these 4 epochs, I will have enough data. So notice that my equation has 4 parameters. With 4 parameters, theoretically, you just need 4 data points in order to calibrate the parameters. So in 4 epochs, we got enough data to parameterize the equation, and then to calibrate the equation, and then from that point onwards, we just enforce the partitioning, and voila, the fairness parameters all come down. So that was applying the equation to traffic. The latest thing that I did this year was memory allocation to minimize task latency for operators. This streaming application. So with streaming applications, you have a request. Okay, so let's say it's an auction system, or it's some kind of bidding system, or some kind of or let's say you take CCTV footage, and then you're trying to detect intruders. Okay, so the packets are coming in constantly, and then you go through some set of operators, and the operators will do image identification, pattern recognition, etc. And then come out and say, no, there's an intruder, or there's no intruder. So that's the idea. Each operator runs a bunch of tasks in parallel. And then the question is, how do I allocate memory to these tasks? Notice, for example, here you have 2 streams coming into the same operator. So the operator has to figure out how much memory to allocate to each one of them. Okay? So for me, the interesting thing about this particular application is the comparison to the so-called churn approximation. If you are familiar with cache misses, you will have heard about the churn approximation or the fade-in approximation. It's used all over the place, and I myself have never used the churn approximation because I believe in my equation, of course, more than believe in the churn approximation. So for this particular application, I did a comparison, and voila, if the application has updates, then the churn approximation actually is very bad. The data points are the crosses here. My equation fit the crosses, but the churn approximation has this the red points, and they don't fit the black points. This is the case with the updates. The other thing that was different was non-uniform object sizes. With non-uniform object sizes, the black points are the measured misses, and then but the red points are the ones that you get. With churn approximation, you can calibrate the churn equation with just, I think, 1 or 2 data points, and then what you get is this thing here, which is way away, far from this one. Whereas the cache miss equation can fit this thing. So to me, the interesting point here is that the churn approximation, something that is strongly believed in the literature, actually doesn't work for this case. For non-uniform object sizes with updates. For my equation, I don't care. Okay. Non-uniform object sizes and updates and okay. So we tried we use the equation to do the cache to allocate memory for the operators, and then this is the baseline data. This the one, the blue one are from Cher, and the red one is using the equation. And not only are the rate points lower than the other two, the rate points reach the minimum stabilized before the other. Okay, I don't want to bore you anymore. Where do we go from here? Seems reasonable to go to GPU caches. If you are interested in using the cache-miss equation and be famous for the next 50 years, try this one. 50 years from now, there will still be caches. So if you work on caches, you have a chance to be remembered 50 years from now. If you work on deep learning, I don't know. Okay, so GPU caches. I've not shown you any data, any paper about hardware caches, but I know it works for hardware caches because some years ago we tried it on L2 cache and it worked. The problem was that the project was done by an intern, and the intern finished before the project was ready, had enough data to be published. So I never had a paper using the equation for hardware cache. Now, if you want to do it for a hardware cache, try GPU, where everybody is interested in GPU, right? Right, that curve. Next thing, similarity cache, which I discussed with Daniel yesterday. Beyond that, who knows, right? Like I said, you will always be caches. Thank you.
Questions? Comments?
Well, I was just wondering if there's any particular case or weakness of the top-down approach that the bottom-up would perform better, and if so, could like a hybrid approach be the way to go?
There are no real systems for which the bottom-up actually fits. The bottom-up requires, for example, some idealized replacement policy. Let's say, even LRU, right, is idealized. In practice, you never actually implement LRU in its ideal form. There are always prefetching. There are always you don't look that far into the stack or anything. In real life, the replacement policies are never absolutely LRU and never LRU alone. There are always some other thing. So I don't believe that bottom-up modeling would actually fit any real instance. If you look into the literature and look at any paper on bottom-up modeling, and they show you experiments that show that the equation works, the experiments are almost surely simulation experiments, trace experiments, etc. For me, I don't do that. Yeah, for the network caching, I can't help it, right? Because I don't own the network. I can't do this network traffic on the real network. But for the others, like on garbage collection or on the streaming operators or on this cache, they are just real measurements.
Thanks for the talk. Can you tell, Prof said something, but this equation, I assume, comes from a simplification of the model, no? There will be perhaps some assumption. Can you tell us something about what are the assumptions at the core of the...
Okay, so this is the equation. So in order for the equation to be able to capture the interaction between the reference pattern and the replacement policy, it has to somewhere in there have something that combines the two of them. And it is this invariant that combines the two of them. I grandly call it an invariant. The idea is that this equation here, this approximation here, must work for all reference patterns and all replacement policies. Okay? Once you have this invariant, you add Little's law. So what you have is a black box of, you think of it as pages, let's say. You have pages go in and out, and then maybe you get replaced and go to this, and then it comes back in, etc. If you think about it that way, then once you have the invariant, you put in Little's law, you get that equation. So that is at the high level. Okay. So what is this invariant? This invariant has these three parameters here, with three variables here. T-ran is the average time between enter into the black box and coming out of the black box. T-disk is the time it stays on the disk. Once it goes to the disk, it stays there for this amount of time before it comes back into RAM. And then R is the average number of time a page is read from disk. The original derivation was for disk traffic, so all these variables are in terms of their set. Okay, what? So now the question is, where did this invariant come from? This invariant idea is very simple. It says that there are two likely scenarios and two unlikely scenarios. The likely scenario is that if the R value is small, if the pages are read only a few times, then it must be that when they come into memory, it stays there for a long time. It stays there for a long time. That's one possibility. The other possibility is that there's a lot of replacement. There's a lot of replacement so that you get read into memory a large number of times. If that is the situation, then it must be that the T-RAM value is small. Every time you come in, you stay for a short while and then you get thrown out. So with this and with that, you have that. Right? If R is small, then this whole thing is small, then this whole thing has to be large. Or if R is large, then this thing is small, and that thing has to be large. It is unlikely that the R value is small, and then the T-RAM value is also small. It's unlikely that the R value is large, and then the T-RAM value is also large. Those are unlikely. So this invariant here captures just two ends of the possibility space. And then essentially, the invariant is interpolating from that two ends. And God knows whether that interpolation will work. But then when I was doing this, I was thinking about, you may be familiar with, in queuing networks, there was this approximation, I forget, what's it called? There was this approximation that works at the two ends, and then it's an interpolation into the middle. And it turns out to be a pretty decent approximation. So I was encouraged to adopt the approach, which is to make sure that it works for the two situation, two ends, and then just interpolate in the middle. And with that, it is. That answers the question?
Yeah. Perhaps then I have a comment, no? So you have these parameters that, if I understand it, you estimate from traces, no?
So the equation is based on 4 parameters. You need to calibrate those parameters, so you need to have a sample to calibrate the 4 parameters. Where do you get this sample to calibrate the 4 parameters? This is one possibility. In the case of, I forget in which of the papers we demonstrated this. So if you do a bottom-up modeling, under bottom-up modeling, there's an approach called the Madsen stack, which assumes independent references, LRU, etc. If you have all those assumptions, then when you have a trace, based on that trace, you can calculate the probability of a miss for any given cache size. Okay, so we start when we want to calibrate the equation. When we start up, we bootstrap it. We start it up. You go with the Madsen stack. You collect the reference pattern, and then based on that what you have collected, you calculate the probability of a miss for that cache sizes. That gives you a few sample points. You don't need many. In my experience, 10 sample points is plenty. Okay. So you have say 10 sample points. With those 10 sample points, you calibrate the curve. After you have calibrated the 4 parameters, from that point onwards, now you apply the equation to do your cache partitioning, etc., etc. And based on that, you're going to generate new samples. And based on the new samples, which no longer make assumptions about LRU, blah, 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 now you are on your way.
So if you accept this provocation, why is this not learning?
Huh?
Why is this not learning? You take the
Why is
data
it learning?
and
I'm
you
not
tune
saying
on.
I'm not saying it's not learning.
It's even online learning, even worse. I mean,
It's not deep learning.
it's not too deep.
But that is learning. It's still
How many trillion parameters are there? How many? How many more?
Was a joke.
Yeah.
Thanks.
Other questions?
It's also a comment that you mentioned both chain approximation, Feigen approximation. You said this is a long-lasting problem, and indeed, rediscovered Feigen approximation. But finally, people start giving credit again to Feigen, right? So even if someone forgets about your contributions, eventually there will be another person to go back and still recover, right? So I think just this comment that I agree. I think Feigen's work is like more than 50 years ago, right? And Che approximation is around 20 years. So
It gives me hope. It gives me
Yes.
hope. The equation has been sitting around for 25 years. And when I presented the streaming thing in Downstart sometime early this year, Florence Chuchu commented, he was in the audience, he commented, you don't advertise this equation enough. So I'm here advertising it. But I feel very sad that I'm emeritus now and still the equation is not gaining traction. Okay, I will wait for another 25 years. Okay? And like I said, I'm confident that 25 years from now there will still be caches. And if there are still caches, my equation is still has a market. So we'll see.
I think there's just the GPU paper. What is missing? If you could publish.
So please, if you have a student who's working on
Students,
this,
yeah.
please try my equation. I need a viral paper.
Yeah.
yeah.
Thank you.
Any more questions? Thank you, Tay.